everybody. In this video, we're going to talk about a phenomenon that would definitely end up on any list we wrote down of the most important physics concepts for the modern world. It's called magnetic induction. Magnetic induction is a process whereby we can use magnetic fields to create electric currents. Now, why might this be useful? It turns out that magnetic induction is one of the fundamental physical ideas that allows us to generate electricity. And I think it's probably fair to say that as far as the modern world is concerned, generating electricity is one of the most important pieces. So let's see how this works. Let's start with a simple example. Suppose we have a single loop of wire with a magnetic field that is pointing through it. Now, this setup on its own will not produce any sort of current. But before we see how we can produce a current with a similar setup, we need to define another idea. This idea is known as magnetic flux. Flux is a description of something that is pointing through a surface. In this case, because this magnetic field is pointing through the loop, there's a magnetic flux. It turns out it's very straightforward to write down what the magnetic flux is. This is our definition of magnetic flux. Magnetic flux is equal to the strength of the magnetic field times the size of the area that we're talking about, multiplied by the cosine of theta. Now, B and A probably make sense. We know that magnetic fields have a certain strength, and we could calculate, for example, the area of this circle. But what is the cosine of the angle between these? Well, to calculate that, let's draw the exact same thing, but with a side view. The loop of wire is right here. Remember, we're looking at it from the side. Well, the magnetic field points like this. In order to calculate this number, we need to define a direction for the area. To do this, we imagine that the circle forms a surface. Now, this circle is just a loop of wire. It's not filled in, but let's pretend that it is. The direction of this area points perpendicular to that surface. In this diagram, that direction points like this. The angle between the magnetic field and the surface is the angle between the direction that the magnetic field points and the direction that the surface points. In this case, the magnetic field and the surface are pointing in the same direction, and so theta is just 0. However, we could imagine a different scenario. Suppose we tilted this loop of wire slightly. Now the area points in this direction, while the magnetic field still points right to left. So the flux in this case will be different from the first case. So how do we get from flux to an electric current? Well, the answer is an electric current will be created in this wire whenever the magnetic flux through this loop of wire is changing. What's one of the ways we could change the amount of flux traveling through this loop of wire? Well, let's suppose that we were able to control the strength of this magnetic field. Well, let's say that we can control the strength of this magnetic field at will. Suppose that we started turning down the strength of the magnetic field. What would happen to the flux here? Well, the flux would decrease. B would be getting smaller. Because the flux is changing, an electric current will be created in this wire. But how strong will this electric current be, and what direction will it be traveling? Well, to do that, we are going to introduce an idea known as Lenz's law. Whenever you're dealing with magnetic induction, the current that is being created is always going to try to keep the flux where it was. So, for example, in this case, the magnetic field is pointing this way, but it's getting weaker. The current that is created in the wire is going to try to boost that magnetic field back up to where it was before. So in order to calculate what direction the current is going to be taking around this loop of wire, we just have to use the right-hand rule. Because the magnetic field is getting weaker, the current is going to try to make that magnetic field stronger again. So which direction is it going to travel? Well, what would happen if the current was traveling clockwise through this wire? What would the direction of the magnetic field that is created by this current be inside the wire? Well, if we use the right-hand rule, we see that the magnetic field will curl through the wire in this direction. In other words, the magnetic field being created by this current would look like this. But notice this is actually the opposite of what we want. The magnetic field here is pointing out of the board. Because it's getting weaker, the current that is created in the wire is going to try to strengthen it again. But this magnetic field points in the opposite direction of this one. In other words, it's going to be fighting against this magnetic field. But that's not what we want. We want the exact opposite thing. So the current in this case is going to flow counterclockwise. If the current is flowing counterclockwise, the magnetic field that it creates will point out of the board inside the loop. This is what we want. As this magnetic field gets weaker, the current will create its own magnetic field to try to make it stronger. What would happen if we did the opposite thing? Instead of turning down the strength of the magnetic field, we turn up the strength of the magnetic field. Well, remember that the current that is induced in this loop of wire is always trying to put the magnetic field back where it was before. Because the magnetic field is now getting stronger, the current that is created in the loop is going to try to create its own magnetic field that opposes that strengthening. In other words, it's going to try to counteract that strengthening. So the current is going to flow in the opposite direction because the current is trying to produce the opposite effect. Lenz's law just says that the current that is created by the changing magnetic flux will always try to oppose the change in flux. In our first example, we changed the magnetic flux through a loop of wire by changing the strength of the magnetic field. Now let's try a different example. Instead of changing the strength of the magnetic field, let's change the cosine of the angle. Suppose we have this magnetic field here pointing to the right, and this loop of wire that's sitting in the magnetic field. What's going to happen if we allow this loop of wire to rotate counterclockwise? Well, we know that the flux through this loop of wire is going to change. Remember that this angle is the angle between the area vector and the magnetic field vector. If we rotate that loop this way, that angle is going to be increasing. Since the angle is increasing, the cosine of the angle is changing, and therefore the flux is changing as well. But is the flux getting greater or less? Well, let's think about what will happen when this loop of wire bends all the way over. What do you notice about the magnetic field and the area vector in this case? Well, it appears that they're pointing at right angles to each other. In other words, the angle between them is 90 degrees. But what is the cosine of 90 degrees? It's just 0. So the magnetic flux here is 0, while the magnetic flux here is positive. So the magnetic flux through this loop is decreasing as it rotates. So we expect that a current will flow through the wire that tries to increase the magnetic flux through the wire in this direction. Well, what direction will that be? Let's suppose we're looking at this loop of wire from this direction. Notice that this is very similar to the case that we just did. I'll try to draw it. Remember, we're looking at this head on. This oval is supposed to represent the loop of wire bent away from us, like this. So if the wire continues to rotate, then the magnetic flux through it will be decreasing. So the current that is induced will travel around this wire such that it's opposing that loss of flux. Since the magnetic field is pointing out of the wire this way, we expect that the current will travel in such a direction such that the magnetic field it creates will also point out of the wire this way. That direction, based on this perspective, is counterclockwise. So the induced current will go in this direction. Now this may feel a little abstract and hard to visualize. That's okay. It can be tough to think about these things. You just have to do some practice. I promise you'll get it. But how strong is the current that is induced in a loop of wire like this? Well, it turns out that we can write down a very simple mathematical equation for this. Now, I promised we wouldn't do a lot of calculus, but this is the form of the equation. Let's just consider what it means. This just says that the induced current is equal to the negative change in flux divided by the change in time. In other words, if you can calculate how much the flux changes by, and then calculate how long it takes for the flux to change by that amount, and then divide one by the other, you'll get the current. This negative sign is supposed to remind us that the current will always flow such that it opposes the change in flux. This example of a rotating loop of wire is more or less how electricity is generated in many cases. Most electric generators involve something that's rotating. Think about a wind turbine, for example. The wind is causing the pinwheel to rotate. In this example, we also have something that's rotating. The loop of wire is rotating with respect to the magnetic field. We know how to produce permanent magnetic fields. We have things called permanent magnets. So we can set up something very much like this inside an electric generator. Currents like this are actually the result of an electric field that is being created by the changing magnetic field. This electric field pushes on the charges in the wire, producing the current. But it turns out that it can go the other way as well. A changing electric field can actually also produce a magnetic field. So a changing magnetic field can produce an electric field, and a changing electric field can produce a magnetic field. This combination turns out to result in some very interesting effects, and we're going to see those effects as our last topic in next DL.